Here is a brief introduction of the instrumental setup of our microscopic system. The 3D single-molecule active real-time tracking uses a dynamic laser spot to illuminate the vicinity of an emitter and uses the photon arrival information to localize and track particles in real time. Two coupled electro-optic deflectors are used to enable laser scanning in the XY plane following a Knight's Tour pattern, and tunable acoustic gradient lens is used to control laser scanning along the Z-axis following a sine wave. Pixel dwell time for each pixel in Knight's Tour scan is 20 microsecond. So scanning frequency in the XY plane is 2 kHz and scanning frequency along Z is 70 kHz. With X, Y and Z sampling we have a 3D sampling volume with a dimension of roughly 1 by 1 by 2 micron size. In 3D single molecule active real-time, the XY plane is evenly sampled, but along the Z-axis we sample the edges more frequently, which is determined by the probability density of sine wave. This is the sampling density of the system in default setup dominated by the uneven distribution of sine wave. To fully unveil the potential of our system and identify sampling patterns with higher information efficiency, we begin searching for optimal sampling pattern in the XY plane. To perform an unbiased evaluation, the 25 pixels in the default Knight's Tour scan were divided into 6 inequivalent pixels based on distance from center and symmetry. All 62 possible patterns were evaluated using a step test, in which a fluorescent bead was set static and the stage was guided to perform a stepwise motion to simulate actual motion. The average uncertainty of estimated positions was used as an indicator of precision. After comparing all 62 different patterns, we found that a simple 4-pixel pattern, we call 4 corners pattern, gives optimal precision. Here we can see the estimated XY positions from illuminating the particle with default Knight's Tour pattern and the 4 corners pattern. Here density map of estimated positions from one dwelling position was shown in each trajectory, and we can see that the localization uncertainty from 4 corners pattern is significantly smaller. Data from 5 different trajectories show that precision obtained from 4 corners pattern is almost doubled, with 2.6 nanometer uncertainty compared to 4.5 nanometer from default Knight's Tour pattern. The seemingly counterintuitive result that we get optimal precision from off-centered sampling is due to the distribution of Fisher information. Fisher information is the amount of information obtained from a single measurement. And for a Gaussian distribution, which is a good approximate of photon arrival from an emitter in a diffraction-limited system, distribution of Fisher information is bimodal as is shown here. For a 2D point spread function shown here, Fisher information is donut-shaped. And the 4 corners pattern is well overlapped with the high Fisher information areas. We also obtained optimal precision with off-center sampling in the Z-axis. Real-time laser modulation with custom phase delay was performed to obtain different photon arrival distribution along the Z-axis. It was observed that out-of-phase modulation, which illuminates predominantly the edges of the axis, gives optimal precision. Out-of-phase modulation gives 9.2 nanometer precision compared to 18.2 nanometer precision given by default non-modulated continuous wave laser. The roughly 50% increase in precision was comparable to the XY plane. It was observed that off-center sampling contributes to higher information efficiency in 3D. Overall precision in 3D is defined here, and by combining 4 corners pattern and non-modulated continuous laser, we immediately obtain an off-center sampling pattern in 3D and a 15% increase in precision. Fisher information dictates that optimal information density is obtained at a certain distance from center, which is to say, as we expand the size of the off-center sampling pattern, we first get better precision, and then worse precision. This was experimentally observed. Here we evaluated X precision obtained with 4 corners pattern in different grid size, and it was observed that optimal precision is obtained at grid size of 200 nanometer. More importantly, precision obtained at different number of photons for each position estimate is close to theoretically predicted optimal precision, which confirms that 4 corners pattern is information efficient. The scale of point spread function along the Z-axis is roughly 7 times of that in the XY plane. And photon arrival information was collected from different instruments. And these account for the difference in optimal precision in different dimensions. The trajectories of many of the biological processes are non-biased in 3 dimensions. So a method that is comparable uncertainty in all dimensions is needed. This can be achieved by performing localization with four corners pattern and modulated laser intensity in the z-axis. Using different phase delay we can offset XY precision and Z precision, and it is possible to obtain non-biased, isotropic precision in all dimensions.